In this video, we'll learn about the common ways to figure out what are important in a graph using the so-called sensuality measures, so that we can focus on looking at a few relevant nodes instead of all the millions or even billions of items in a large graph. So we're going to look at sensuality. And other more easy way to understand is the notion of importance. So why we want to figure out what is important or what is central in a graph is that so that we can rank all the nodes in a graph. So imagine you have a million or billion node graph. Then we can really look at all of them. So having a ranking would really help. For example, on Twitter, it may be helpful to identify who are the influential or the celebrities so they can follow them, and also to learn about what's happening in the network. And similarly, there's a notion of gatekeeper, which is pretty common and very important on professional social network like LinkedIn. And often these are what we call the people who are connecting communities. So for that reason, often headhunters like to contact these gatekeepers because they are very well versed in different domains and they can help connect people to other people. So having the ranking of nodes would help us with graph analysis, help focus our attention, and it would also help us with visualization and understanding. So for example, instead of visualizing all the 1 million of nodes, we can say just focus on the subgraph formed by the top 100 nodes, or the millions of nodes in the whole graph. So this is actually a notion that has been used a lot in search engine. For example, when you use Google, often you will only focus on the top 10 or 20 pages. And the reason is that Google knows that there's no way you can look at all the million of web pages. So by providing a ranking, it can help you focus on the ones that might be more relevant. So we'll see examples of how we compute these kind of relevant ranking and use it to help us with our analysis. The nice thing about node sensuality is that most graph analysis packages already have them built in. So you can just use them. You don't really need to implement anything. So I also like to point out that there's also edge sensuality. And here we focus mainly on node sensuality. And a lot of the concepts are pretty similar across both measures. So degree sensuality is probably the simplest and most common sensuality people will look at. So degree just means the number of neighbors of a node. So for a directed graph, you will have in degree and out degree. In degree is the number of incoming edges pointing at the particular node, and out degree is the number of outgoing edges. And for undirected graphs, then only degree is defined because there's no directions. And to compute node degree, we can simply do a sequential scan through edge list. For example, with a toy data on the right. And what you need to do is you create an array, let's say, to store the node degree of every node in the graph. And as you step through each edge in the edge list, you just increment the node degree, let's say the degree for node 1 by 1 as you go through the edge 1, 2. And then you increment that number by 1 again as you go through the edge 1, 3. So you only need to do one sequential scan. And if your graph's already stored in SQLite, then it's even better. You don't even need to write any code. And all you need to do is write a simple SQLite SQL else statement. So suppose your graph is stored in a table, let's say edges, with two columns, source node ID and target node ID. And what you need to do is to first create an index for each column. And this will allow you fast access, random access to the edges, all the edges associated with a particular source node ID or particular target node ID. And after that, then you just need to do one statement, a group by statement. For example, here we say select count star from edges group by source ID. So this is how you would be able to find the out degrees of all the nodes. So just one statement and you can compute the node out degree distribution. So really, really easy. So this is another benefit of why using SQLite. So similarly, you can just make a small change. Let's say instead of grouping by source node ID, you can say group by target node ID. Then they'll help you compute the in-degree distribution. And betweenness sensuality is another very popular sensuality measure. And high betweenness score, that means that is more likely to be a gatekeeper in the graph. So here on the right, we use color to indicate the betweenness score. So more towards blue, that means higher betweenness. More towards red, that means lower betweenness. So what does it really mean? So intuitively, gatekeeper means you're trying to connect someone in the network. You're likely to pass through or go through this gatekeeper. Real-world example is, let's say, two people in different communities, and they want to be introduced, then often they may need to go through some middleman, and that middleman would be a gatekeeper. So how do we define this measure? How do we compute that? So to compute that for a node, the Betweenness score for a node, we need to find shortest path in the graph. Essentially, we need to find all shortest paths between all pairs of nodes in the graph. For example, let's say we want to measure the Betweenness score of the node V. Then we need to look at all the shortest paths that would go through node V for every pair of nodes in the graph. So that would become our numerator in this formula. And then for the denominator, we would need to look at all the shortest path connecting a node pair S and T. So we don't really care whether these paths will go V or not, go through V or not. So that means this fraction here is the number of shortest paths that go through V over the number of shortest paths, regardless of whether it goes through V or not. So another way to think about it, that means you want to measure how often this node V serves as the bridge that connects two other nodes. Another popular sensuality measure is clustering coefficient. And it's a measure for a node of how close a node's neighbors are from forming a clique. For example, if all your neighbors know each other very well, then you have a really high clustering coefficient because all your friends know each other. They're forming a lot of triangles. So that's a very close-knit community. So a value of 1, that means, which is a maximum value, that means all your neighbors form a clique, so everyone know each other. A value of 0, so that means none of your neighbors know each other. So that means essentially having a star. You're a center of a star subgraph, where you're connected to all your neighbors by definition, but none of your neighbors know each other. So here, the 3 figures on the right is a very good illustration. So in the first graph here, at the top, the node that we're considering is the blue node, and it has 3 neighbors. And in this scenario, the clustering coefficient is 1, because all the possible edges among the circle, indicated by the black solid line there, they are already present. So that means the 3 neighbors there, excluding the blue node, they are forming a clique. So everyone knows each other. So now if you look at the example at the bottom, the third scenario, where the clustering coefficient is 0. So here, none of the edges exist. So that means there are all the dotted lines there, the red dotted lines. So none of the edges are present. So that means the blue node now is at the center of a star, a 3-node star. And while for the center case, we have a clustering coefficient of 1 over 3. So that means out of the 3 possible edges, only 1 is present. So this is an example showing you what we mean by having a minimum clustering coefficient of 0, where none of the neighbors are connected, and a maximum value of 1, where everyone is connected. So to compute clustering coefficient, we actually require us to do triangle counting. And at the first glance, it may not be obvious why we need to do triangle counting. But if you look at the graph again on the right, and now instead of considering as a counting edges, but think of it as counting how many possible triangles that exist. So in the first case, at the top, you will see that all 3 triangles are present between the blue node and 2 of this neighbor. So for example, the first triangle we can say is a triangle formed by the blue node and the node at the top and then node on the right. And the second triangle will be the blue node, the triangle on the right, the triangle at the bottom. And the third node is the blue node, triangle at the top, and triangle at the bottom. So here we see all 3 triangles. So that means that counting triangles is another way of thinking or considering like whether we are seeing an edge or not. So counting triangles are expensive. In general, that means we need to do something called neighborhood intersection. And fortunately, there are a number of approximate algorithms to compute that. And one of them is really clever, and we can compute triangles really, really quickly. So this leverages the formula where it says the number of triangles in a graph and it's exactly the product of 1/6 times the sum of all the eigenvalues cubed. So this would give you the exact triangle counts. Actually, this formula has been known for a long time. So that means as long as you're able to compute the eigenvalues of the graph adjacency matrix, you take the cube of them, you add them all up, and take 1/6, and then you get the exact count. But remember that from the previous video, we tend to see parallel distribution in the eigenvalue distribution. So, and also that means we will have a very highly skewed distribution. And that means we only need to compute the first few eigenvalues instead of computing all of them. So this is a reminder of looking at the power law. So here, vertical is the eigenvalues, and horizontal is the rank of eigenvalues. So that means at the towards more to the left, those are the greater eigenvalues. And very quickly, you'll see that once you step to like 10, 20, or even 100, the eigenvalues drop really, really quickly. So remember that in the formula, we need to take the cube of the eigenvalue. So that means for smaller eigenvalues, taking the cube of it, it becomes even smaller. So that means we can just ignore them. So that means in practice, what we can do is just keep the top few, maybe tens of eigenvalues, and we can get a significant speed boost. For example, in this chart, we're showing the accuracy versus speed up plot. So vertical is the axis, so that means how close our approximation of number of triangles to the real number of triangles. And horizontal is the speed up. So here, unsurprisingly, we will expect to see up to like thousands of times faster, and while we're still able to maintain a very high accuracies. For example, we can get about 97.4 accuracies and at a 1,000 times speed up. There are actually a lot more sensuality measures. For example, what we look at so far is degree sensuality, betweenness sensuality. There are also proximity-based sensuality closest measure, and also eigenvector sensuality. In this video, we learned about a few sensuality measures such as degree, betweenness, and clustering coefficient, so that we can focus on a few relevant nodes to look at instead of going through millions or even billions of items in a large graph.